that's not showing annotations. Maybe the lymphatic system. No, that won't. Maybe I don't have the one with annotations here. But yes, we can. What we would really like to do is to enable you to click on the 3D one and have it tell you.
Yeah.
That would probably require OpenGL, I suspect. Because the other thing too is we want all this stuff to work on an iPad. Reality is the student is going to have an iPad, and that presents its own problems to us because we started off using QuickTime virtual reality. The iPad will show it as a movie, so it doesn't allow any interaction. Thanks for that question, Martin. Any others? Okay, let's turn this back on and to the reconstruction.
Steve?
You have said you are using SQLite.
Yes.
And how big is your database? Or have you more than one database?
We don't keep the images in the database.
Yeah. But your index is the database.
Yeah, the database, it's got 700,000, well, it's probably got more than that, but it's not huge by database standards because it's, see, the TIFF images are our database as well, when you think about it, because they're the map from the XY position to the 24-bit value. So the stuff that we have in SQLite tends to be the name of the structure, where to find the TIFF image, where to find the JPEG, the base JPEG it sits on, that sort of, so they're not huge by any means. I know Steve Huntley has done some experimenting with putting images into SQLite as blogs, and he gets all excited about it, but I don't know what he was actually doing. Do you remember?
Yeah, it was, he was doing that spatial mapping technique. He was actually putting every pixel into the database and doing a query so that he can, using SQL, query the image pixels to get a result back. It seems bizarre, like it's not meant to be put together that way, but he was successful and he was able to make a high performance image querying system using SQLite, storing pixels in itself. Yeah. I have to see it for myself yet.
Yeah, the more perverse it gets, the more excited we get, so. All right, we've done that. Now, VScope. It's a virtual microscope we built out of open source components. One of the main components was IIP image, which is from the Louvre in Paris. It's a really, really good image processing, image presentation system. It comes with a viewer that's several viewers based. But there was one called IIP Moon Viewer, which is written in JavaScript. So basically, you've got an advanced high-performance tile image server system, and then you've got a viewer, web-based streaming and viewing of those tiled images. It can handle gigapixel size images, so that got us all excited. And it runs as multiple FCGI processors under, well, you can use just about any web browser, but we started using Lighting. So we got excited about this because we thought we had a collection of histology slides available, histology study of cells. They're microscopic slides which have been scanned at high resolution using a device called an Aperio scanner. We also, back home in Perth, I was introduced to a guy at one of the teaching hospitals who was a dermatopathologist, and he had an extensive collection of these. He had access to an Aperio, extensive collection of images. So we thought what we should do is build a virtual microscope, and we can make that available on the iPad so people can look at students can look at histology. Okay, so this will give you an example of it running. This is a very, very early version of the virtual microscope. It's much more advanced now. But essentially that's a slide taken from the human spleen. And you can see we just had a plus and a minus and zoom in, zoom out. And I want you to note that little area there, because we're going to zoom in on that one just to have a look. That's some sort of vessel, and there's some red blood cells in it. So when we zoom in, we see this sort of thing. And you get an idea of how there. So you're looking at red blood cells. It's interesting, you show this to the anatomy people and they get all excited about this stuff. They're not so excited about the red blood cells, but I am, because I can recognize them. This is an example of a leukemia blood smear. So they get a bit of blood, smear it on the cell, on a slide, and then scan it. And that's actually scanned in oil because it's so high resolution. I mean, those are 5 microns. And if you scan in air, you get a fraction. So the other thing to note at the top, that little green box is what we're looking at here. Apparently these are nasty. They're bad guys. Now this one's really interesting. This is almost art. This is a very rare primary cutaneous intravascular anaplastic large cell lymphoma, T-cell phenotype. Okay, why am I showing you all this stuff? Because there's no TCL, TK in V-scope in the virtual microscope. Well, the reason I'm showing you is a thing called the Harvey collection. In 1955, Dr. Thomas Harvey was a pathologist who conducted Einstein's autopsy after he died in April 55. As was the practice of the day, he kept bits. Now, I'm not going to go into that side of it because it's nothing to do with us. It was done, it was the practice of the day. Apparently, it was the norm, but whatever. So he took Einstein's brain and he segmented it into roughly 170 parts, organised by lobe and then the brainstem. He mounted them on microscopic slides and then stained the slides, or had them stained, to highlight both cellular structure and nerve conductive tissue, 2 different types of stain. And you can read about this on the web, it's out there. But the thing is, he passed away in 2008. And he donated this collection to the National Museum of Health and Medicine, which is in Silver Spring, Maryland. Now, the Chicago Museum is sort of a digital outpost of the National Museum, and the director of the National Museum approached Mike and said, how can we help preserve this collection? This is a valuable collection, not just US significance, worldwide significance. Some of the slides were deteriorating. So back in 2011, we decided that, well, you know what, if we had these slides scanned, we could preserve them and display them using the virtual microscope. So we shipped them out Mike took them out to Perio Technologies in California. This is Dan, the scanning man, and that's the Perio scanner on the left. So this box, these cigar boxes, contain the slides. Or some of them.
What are the size of the slides?
1 by 1.5 inches. 1.5 inches. Yeah, some of them are 1 by 3. And I'm glad you asked that question because Aperio, when we were there, they showed us they'd actually made a new mount so they can scan the high resolution slides, and they're out there at this moment being scanned. Probably be finished end of July. So they had to modify their machine to scan the larger ones. Then my wife Sue and I and Mike Doyle, who's on the left, went and picked up the slides. So we had 5 2-terabyte drives with all the data because we got the raw TIFF images from all the scanning. I mean, each slide's 90,000 pixels that we scan it at, so 90 by 60, I think it was. There's a book called Driving Mr. Albert, which was infamous book about a guy who drove across America with the old pathologist with Einstein's brain in the back. Well, we sort of did the same. The slides containing his brain were in that case. We drove, anyway, we had 10 terabytes of raw images. The thing that at the time I thought was quite interesting because this Jeep, rental Jeep, probably has the same bandwidth as the internet did 20 years ago. And then we flew back to Chicago. If only people knew what was in the case. Now, aluminium case with glass slides doesn't show up when you x-ray it, nothing. We had all the paperwork, but I really did wonder what would happen if someone said, what's in the case? And then the slides were returned with much relief to their repository in Maryland. Alright. So what do we do with these images? We've got 10 terabytes. Well, we had to turn them into JPEG 2000s, which is the image format we use on the IIP image server. So there were 348 images, up to 30 gigs each, a total of 10 terabytes. And this is where TCL comes in, because the automation of our system administration on all the servers, the collation of the data, the documentation we received, all of Harvey's notes, so we wanted to correlate that. Organising all that stuff was done using TCL scripts. We organised it into regional lobes, so that's the, I'm going to try and impress you here, but I probably won't. Parietal, occipital, frontal, and one other, and the brainstem. Just having the whole thing organised through SQLite was great. As you can see, we use TCL for automation. I can't hold that sort of information in my head, so if I script it, I can always come back to it and rerun it. Then we had to decide how we're going to deploy this thing. We decided to deploy it on an iPad app, mainly because to make it widely available and to hopefully recover some of the costs involved with processing and hosting this thing, because the museum is not for profit. It's not a commercial enterprise. So the other thing with doing it on an iPad app is that, one, every student seems to have one these days, certainly in US colleges. The other thing, though, is it's a fixed display size. That makes image processing a lot easier for us. We found that IIP image, at least as it was then, was extremely sensitive to the size of the image that we were hoping to display. And just about every Android device seems to have a different resolution. So we went with the iPad. The other reason was we hoped to recover some costs through it, and the iTunes App Store has got all the infrastructure to do that. So the next question became, how do you represent a menu of 348 slides? Now that actually is a rather tricky problem, because a traditional menu is too, who wants to look at a menu that's got, load, then section, brain part? It's not fun. And Colin McCormack, Colin on the chat, mentioned to me this really interesting piece of software he's seen called R4JS, which is a JavaScript tree widget. And I thought, well, I can use that to actually represent the hierarchy of information. Now, I've got to tell you, this thing is a pain if you're using it on a desktop where you've got to move the mouse around, but it's great on a pad, because when you actually display this, it's like a planetary system that moves around. And so I'll show you later, just I didn't want to run the thing and soak up all the bandwidth. But what's really cool is we can now break it down into the regions. Temporal was the one I forgot. Occipital, particular part. These parts are as the pathologist guy decided they'd be numbered. And then we've got two types of staining here. A nasal stain, which shows you the neurons, and then a myelin stain, which stains the connections between neurons. And we wrote this dynamic menu in JavaScript, but the really cool thing was, I don't want to write JavaScript if I don't have to. I already had a database of all the parts. All I did was write a TCL script which generated the JavaScript. And then if we change things around, I just change the data in the database, rerun the script, the JavaScript's rewritten, inserted into the iPad app. The iPad app itself is a hybrid app. It's basically mostly just a web browser embedded in an Objective-C app that does callbacks into the Objective-C. All right, so here's an example of the Harvey, of the Einstein brain app running. You can see you can go back to fully zoomed out, plus or minus. That allows you to send it to someone else if they've got the app. They tap on an email and they see exactly what you saw. Down here we've got some objective stops. Those of you who are familiar with microscopy, you realise that you have standard stops at like 10, 20, T times magnification. Well, that doesn't make any sense in terms of this digital one. So we did it as a percentage, 3%, 6%, 25 and 100% zoom. That green box shows us the extent we're seeing here. So once you navigate all the way down, so at the top we can see part 184, slide 95 occipital, and this is a myelin stain. So let me give you a demo with a bit more detail. We'll start off, there's all the regions. You tap on one. These things are jiggering around, so it's good for kids and think it's a bit like a game. I've tapped on occipital. I've tapped on part 186. Tap on myelin, and then I'm going to pick one of the slides. I tap on nasal, I can pick another slide. This is a nasal stain. You can see, again, the little green box tells us what we're looking at, the entire thing. Now if I just tap on 3%, you can see we're looking at that region. And then we're at 6%, 25%, and then 100% zoom. And those are Einstein's neurons. Somebody last night I spoke to, I promised to show them Einstein's neurons. Now the thing is, I was interviewed by the PBS, the Public Broadcasting System in the US last year when we released this, and they asked the question, what do you think Einstein would have thought of this? And I actually think he would have been excited, because he was all about discovery, and he didn't want his remains to be made a circus. But he did want to further science, so I'd like to think he would have been excited about the potential. The thing about Einstein's brain is that the studies up until we released this app were only done at the macroscopic level based on some photographs that were taken. Now researchers are able to look at this at a microscopic level for the first time. And not just researchers, anyone who's passionately curious. And passionately curious is how Einstein described himself. So that's a nasal stain showing the neurons. Go with the myelin stain again, you'll see as we zoom in. The little box on the top right is getting smaller. And you can see, you're not seeing the neurons so much, but now we can see the connection. So, two ways that they might be used for research: neuron density, how many neurons you've got size, and then how it's connected together. But again, that's not for me, I'm not a neuroscientist. Alrighty, so how did this server infrastructure work? Well, basically the iPad screen is 1024 by 768 pixels. When we tile it, you end up with 12 tiles to fit in that size. Each of 256. But the way IIP image works is it actually brings in all the tiles around as well. So as you're dragging your finger to scroll around, it's pre-filling its cache, so to speak. So what we wanted is something that's going to go. We didn't want to pre-render all of the images at that stage because it was a big problem. So what we did is we put a bunch of four-core linodes. We put a node balancer on front, which is a linode facility that essentially, well, in our case, we used it to round robin the connections so that it's any one user is probably hitting all of those at once. 4 cores, 8 of the things, that's 32 cores being balanced. Theoretically, one user, it could all happen in parallel. But then we put Cloudflare on the front. Now, who's familiar with Cloudflare? So if you're not, look into it, cloudflare.com. It's a US company that offers, it's like a web proxy, plus a whole lot of other things. But the really cool thing is they do the caching for you. So all we needed to do was to have the user go to a particular slide, particular section, have all of the tiles brought in, and then the next user gets that straight from Cloudflare. It doesn't touch our server at all. So with this arrangement, we only ever had to serve a tile once. And it was just fantastic to actually be watching the logs, have someone testing, browse around, the next person go in, and there's nothing hitting our servers. This is cool, but then we got the request, can we provide a standalone version of the Einstein app to run at the National Museum in Silver Spring, Maryland? And there's a problem, there's no internet connection available for various reasons, so we had to 60-inch display, we had to provide a computer for that, but we had to pre-render all of the tiles. Pre-render 50 million tiles. 350 gigabytes of data. Well, what we Steve started building the machine for it, and I started writing a TCL script that mimicked the client, but it mimicked the web client. But all it did basically is just fire off requests in parallel and used event-driven file events basically to recognize it. I just used the HTTP package and fire off as many of these things in parallel as I could. When the tile came back, I just shoved it in a folder, in a directory. And then we used an SSD because we thought this would be really, really good for performance. Well, yes. Here's the machine that was doing the rendering. This is one of Steve's machines. Note the fan. Okay? You sort of... the problem is we destroyed the SSD. Totally destroyed it. It just kept dropping out, and he was putting new versions of the Linux kernel in. And in the end, what did us in was that we ran out of binodes. Each tile is 256 by 256. And you got lots of them. We just ran out of binodes. Unfortunately, we didn't realize at first because the message file system full. And I'm looking, space there. But anyway. So rather than do that, we reverted to an enterprise quality hard disk. And it ended up taking 1 month pre-rendering. There was a little problem in the middle called Hurricane Sandy, but apart from that, 1 month of pre-rendering, 350 gigabytes of tiles out of 50 million tiles. And the tiles are served up because we no longer need the IIP image server on the back end. All that happens now when the client asks for a particular tile, it's just grabbed off the disk and served out. So how do we do that? We stuck with Lighty, the web server, and a TCL script that used SCGI, the simplified CGI, and that basically gets the request, pulls the file off and returns it. And I think we're running it with 3 or 4 in parallel or something like that. But that doesn't matter anyway. The point being is we experimented and we actually designed the techniques for using TCL as an SCGI scripting language in that particular project. You could use it by Lighty or Nginx or anything. And that works just fine. In fact, that's a photograph from the museum in Maryland of a gentleman staring at the display. And you can see, it's just basically a big iPad, 16-inch iPad. And the exhibit's live, and we haven't heard anything negative about it, so we assume it's working. Going forward, we're pretty much not using TCL HTTPD anymore. We're not using Lighty, we're using Nginx with TCL SCGI scripts in the back end. And on all the projects we work on. And that's really working really well. No typical HTTPD, no WUB, no Wibble, no Rivet, no AOL server, none of that stuff. Why? Because our domain is solving not the web server problem, but solving, in this case, the museum problem, the business problem, and the startups we're working. So our view is that SCGI means simple scripting for the web. And SCGI and TCL means all of the skills that we've got. It's automatically scalable. There's no interpreter startup cost. Nginx in particular is good at firing up as many of these things as you want. It's a HTTP server and a reverse proxy. It solves the C10K problem, which means it can scale up to, C10K is 10,000 concurrent transactions, something.
Clients.
Sorry?
10,000 clients.
10,000 clients, yeah. I think this is, yeah. It's event-driven. It uses, it doesn't use threads. So that's always a good thing to me. I mean, to me, threads are a necessary evil, but not always necessary. But the point is, we can write our scripts without, yes,
How
Neil,
many clients do you have concurrently for this application?
for the Einstein one, I have no idea. So I can't answer that one. I can
Yeah,
find out.
that's why I was.
Yeah, no, I would doubt that we'd have 10,000 clients concurrently because Cloudflare will be.
Yeah, there's some works. I'm just trying to understand the resource behind SCGI versus all server.
Oh, okay. Well, look, the thing with SCGI is its benefit is that you can write a script the same way as you'd write a script to run on a desktop. Read from input, process right from output. And you let the web server worry about scalability. You don't have to worry about that at all. And that's the beauty of a CGI approach. So if you like, you can write in the way that we'll think, which is linearly. And let the web server start up as many of these things as it needs to serve the various clients. And if you've got a decent back-end database, then they can be sharing information too. But no log files, mutexes, all that stuff goes away. The thing is, Nginx is flexible, really flexible. It's where most of the buzz is about web servers at the moment. So we can write on the back of that. So you can have them connected via Unix domain sockets, you can have them connected via internet domain sockets, you can have multiple configurations using both. They're still calling TCL scripts at the back end, so that's what we care about. So, a few quick things on the exhibit space, because this is actually fun stuff. At the exhibit, at the museum, underneath each of these 60-inch screens, there's a 25 60-inch screens around the display area. Underneath each is a Kinect sensor. You're familiar with the Xbox 360 Kinect sensor? So we commissioned Andreas Cupraes to build a TCL binding for the Kinect sensor. It's called EuroTcl. And then wrote a bunch of scripts to detect the presence of a person standing in front of the display. So what happens is the display, there you can see the displays around there, and you've got the content is sitting there waiting with a big picture for someone to come along. This one has started scrolling, so someone's walked past it, that one there. And as you walk up to it, the Kinect sensor can detect that there's a person there, and it starts the exhibit going. And you can see a strange looking fellow. Anyone recognise the person on the left? Yeah, that's Carol Lynn, who's who does all the management of the TCL conferences in the US. But here you can see an example. Because we're standing there, and there's the Kinect sensor. It's detected someone's there and it started the exhibit scrolling. And EuroTcl can actually detect a lot of other things as well. You can see here that you've got various points that it's detecting. So there'll be more and more work done on just using that to do more advanced things. Like we could actually take a metric on each person, and without actually knowing the identity of the person, we could recognize as that person moves through the museum just by the dimensions across the shoulders, the length of the trunk, and so forth. So we could actually have a customizable exhibit that adapts as you move through the exhibition space. But one of the real cool things, I got this weird idea in the shower one day that I could use this to track people that were walking past the sidewalk. And welcome, this is Jibber. Jibber is the skull from the visible human, but above here is the Kinect sensor. And what it does is I've got about 120 line tickle program, TCL program, and as people walk down the sidewalk, the skull follows them. And if they stop, the jaw goes yabba yabba. So that's 120 lines of TCL.
And that's supposed to make people come inside, isn't it?
Yeah, well, I'll tell you what, when we first tried it, we noticed that there were people walking down and the parents head down. And there's these little kids standing around pointing, so they must have said, "Mum," and looked at me. Anyway, 120 lines of TCL TK, so that actually is a TK program. Alrighty. Now the fun stuff. We have 25 minutes left of my time, which is what I hope that we have get on to the new ones. So I talked about the 3D reconstruction, so we start with these 2D sections. We go to 3D reconstruction through ray tracing, and that ends up with a QuickTime object movie. I mentioned we use those Cyrex. But what if you didn't want an object movie? What if you actually wanted to print one of these anatomical structures? Well, what we have to do is surface reconstruction of some sort. And that's done using various technologies, various techniques, I should say. Probably the most common is called marching cubes. It's well known, the authors of ITK invented it. And what you end up with is some sort of surface model. The most typical one is called STL, or stereolithography. You want to come up, Steve, and we'll get ready for your part. And so you end up with a surface model. The trouble is, and that's just basically triangles, vertexes, faces. And because we've got relatively high resolution, it actually gets quite large. So we actually then have another step which we call mesh decimation, or it is called, we don't call it that. We call it simplification. But it just means simplifying reducing the number of faces on the model so we get down to somewhat more manageable, but still look good. And then I end up with an STL model, which I ship to him, and he starts talking.
Okay, and my name is Steve Redler. Most of you know me already. I've been here last year, and I'm a board member of the TCL Association in the United States. And I helped put together the conference there. Anyway, anybody do 3D printing here yet? Nobody doing it? I'll go one person? Okay. Anybody interested in the technology? Everybody's got to be interested, right? So, of course, it's the joining of the hardware and the software that makes it really interesting. It's a great hobby in itself, but for me, it was always, it's just the aspect of just building something and making it work, doing stuff. When Steve approached me with some of the interest in doing this kind of work, of course, with my background in electronics and system administration and building servers, I mean, just to talk back to your point of the one server with the fans all over it, you know, I told Steve, oh, it's no problem. It's just a server, it's Linux, everything just works. No, yeah. I had more problems with that job, rendering those tiles. It was just failure. I mean, all the errors, because it's all new hardware, the kernel has some untested drivers in it, and so we're working on basically cutting-edge kernels just to get this thing to render. And, so that was some interesting aspects of it. Anyway, so now we get into the idea of if we want to print a structure in 3D, what do we have to do? So I've already got the equipment. I built my own 3D printer. Had a hard time getting it up and running because there's a lot you have to learn in order to understand each of the components and how they interact and make either a successful print or a failure. And the failures are very common in 3D printing. So the first part is when you have a stereolithography file, which is the outside mesh representation of an object. We now have to take that 3D object and slice it back into slices again, what Steve started with. We have to re-slice it because as we print it, we're going to print one layer at a time as we build up the model. So I'm using an open source program called Slicer. And this is a combination of Perl and Python. I don't like it, but it works well. So I hand off to that. As a note, there is somebody that posted on the wiki a TCL, a very primitive TCL slicer